Hello, everybody. My name's Eli Shuko. I'm a second year graduate student here at Illinois State University in the hydrogeology program. Today's talk is going to be about in relation to my thesis research, and it was done in collaboration with my thesis committee, Dr. Eric Peterson, Dr. Catherine O'Reilly, and Dr. William Perry, and the LEA lab manager here at Illinois State, Jack Wang. Today's talk is going to be in relation to total suspended sediment and phosphorus transport in response to storm events in an agriculturally dominated watershed. So to get off, what's the big deal? Increased sediment introduction and increased sediment nutrient introduction and transport in streams has a large impact on water quality and ecological diversity. The EPA estimates that this causes around $16 million in environmental damages a year, including reservoir filling, and it can also affect the reproduction rates of fish and other aquatic life. Specifically, the introduction of phosphorus is a main driver of algal blooms, and when found in excess, can lead to large algal blooms and the formation of dead zones. So this image on the bottom here is from NOAA and displays an algal bloom that took place in the Great Lake Erie in 2017, where you can see this light green area here representing the size and scale of this algal bloom in this Great Lake. So sediments and phosphorus come from a couple different sources, and they have some interesting behaviors. To start out, turbidity is an optical measurement of water clarity and can be used as an indicator for water quality as well as an estimate on the total suspended sediment content found in the water. Phosphorus, however, is generally found in two phases. It comes in a particulate phase and a dissolved reactive phase. The particulate phase is the solid phase of phosphorus, and in this form, it's able to cling onto and adsorb onto sediment and mineral particles, which can be explained kind of by this figure down below. Here we have a mineral particle, and these red circles and dots represent phosphate ions that are adsorbing onto this sediment particle and allowing it to be transported along with the sediments as they move downstream. These introductions into streams tend to be from storm events and driven from overland flow as well as tile drainage here in the Midwest. These pictures on the right represent some of the field conditions explaining the turbidity that we see at the 6 Mile Creek study area. The top representing clear water and non-turbid conditions where you can actually make out some of the bottom characteristics of the stream, and below facing the same direction at the stream, but after a storm event where here we have bank full flow and much more turbid conditions taking place. So a way to gain insight in the relationships between turbidity and total phosphorus is to look at the concentration discharge relationships that are taking place in the watershed. And a way to do this is using a technique known as hysteresis. And hysteresis is a concentration discharge relationship where the concentration variable differs on the rising versus the falling limb of a hydrograph. These hysteresis patterns generally form loops and are described based on their rotational direction and their magnitude, and include figure 8 shapes, clockwise rotational patterns, and counterclockwise rotational patterns. Below on the left here, we have a figure from Williams 1989 displaying an example of clockwise rotational patterns, which take place when the concentration variable reaches its peak concentration before peak discharge. When plotted against each other with discharge on the x-axis and concentration on the y, clockwise rotational pattern can be observed. However, if the concentration variable reaches its peak after peak discharge, when plotted against each other, once again with discharge on the x and concentration on the y, counterclockwise rotational pattern can be observed. These rotational patterns can be further defined and expanded on by calculating a hysteresis index. And a hysteresis index is calculated by taking the concentration at the rising limb and subtracting it from the concentration on the falling limb. This is done at 5 to 10% intervals of discharge throughout the storm event. Then those values are averaged to get an average hysteresis index for a given event. A positive hysteresis index correlates with a clockwise rotational pattern, indicating that our concentration variable is peaking before peak discharge, and can indicate that the sourcing of these variables, in this case phosphorus or sediments, are from near stream or in stream sources. However, a negative hysteresis index would indicate counterclockwise rotation and indicate that the sourcing of these variables are coming from more upstream and out of stream sources. These loops can also be expanded on by calculating a flushing index. This provides some insight onto the slope or the gradient of these loops and is calculated by taking the concentration at peak discharge and subtracting it from the concentration at the initial discharge event. A positive flushing index value would indicate a larger concentration observed at peak discharge than at the initial discharge of the event and indicate that you have a concentrating effect or a flushing in of these, in this case, phosphorus and sediments into your stream. And a negative flushing index would indicate that you have more of a dilution effect taking place and a washing away of these variables in the watershed. So the research questions of this study are to try and address, do turbidity and total phosphorus follow similar transport behaviors in the same watershed? And is the flushing index and hysteresis index observed during storm events among turbidity and discharge and for total phosphorus and discharge similar? And how do these index values vary across seasons? So this study site took focus at 6 Mile Creek and its watershed. This is part of the Evergreen Lake watershed located in McLean County, Illinois. This watershed is 106.5 square kilometers in size, and the land use is predominantly agriculture, with 87% of the watershed being dominated by row crops. This image on the right here is my study site figure. The red highlighted state is the state of Illinois, and the yellow star representing the Evergreen Lake watershed. Down below, we zoom in on the Evergreen Lake watershed. This blue highlighted line represents 6 Mile Creek, which flows into Lake Evergreen, which is a municipality drinking source here in Bloomington Normal, Illinois. And about 0.8 kilometers up from this lake, we have this red star, which represents the sampling site used for this study. Data is available for this study from April of 2016 through January of 2019 and is available for the variables of turbidity, discharge, and total phosphorus. So the 6 Mile Creek study site collects data on a 15-minute interval for both turbidity and discharge. Water samples are also collected using an automated water sampler from the site and are analyzed for their nutrient and major ion concentrations. These water samples aren't collected at 15-minute intervals, but are collected based on a certain percent change in turbidity observed from the turbidity sensor in the stream. The data that was available for these variables was normalized by event to allow for comparisons between both large and small scale storms. And so this normalization was done by taking the discharge observed at a given time for the event, subtracted from the minimum discharge for that event, and divided by the range of discharges observed during that individual storm. This was done for all discharges in an event and produced a value ranging from 0 to 1, with 0 representing the lowest discharge observed for the event and 1 representing the largest discharge. The concentration variables, turbidity and phosphorus, were also normalized in the same fashion, where the concentration variable replaced discharge in the equation. These normalized variables were then plotted against time to get a sense of behavior over the duration of the event, and the normalized concentrations were plotted against normalized discharge to get an idea of these hysteresis patterns and behaviors for every storm. So there was some correlation observed between turbidity and total phosphorus during this study, and for the duration of the study period, 791 data points for both variables were available. And the correlation between these variables was found to have an R-squared value of 0.66 and an R value of 0.81. This relationship can be classified as a strongly positive correlation and can be observed in this figure found below, where we have turbidity on the x-axis and total phosphorus on the y, and the relationship being generated by this best fit line produced here. So based on the strong correlation observed between these variables, a linear model to generate high frequency data for total phosphorus was conducted using RStudio. And this model created high frequency 15-minute interval data for the total phosphorus variable, which allows for better understanding and dynamics between the relationship between total phosphorus and turbidity, which is already available at this high frequency, and the generation of more detailed hysteresis patterns for this study. The total phosphorus model used the independent variables of discharge and turbidity to predict the total phosphorus concentrations, and the model produced an R-squared value of 0.73 with a standard error of about 78 micrograms per liter, and is represented by this equation at the bottom of the slide here. So this slide focuses on the most common types of hysteresis patterns that were observed during this study. Going from left to right, the A columns of these graphs represent the non-normalized variables of turbidity, total phosphorus, and discharge, and plotted against the duration of the storm event. Column B represents these same variables, but now they're normalized and plotted against the same duration of the event, so they all have the same scale here. And then the normalized concentrations, green being total phosphorus and red being turbidity, are plotted against normalized discharge to get a sense of these hysteresis patterns observed during the study. Going from top down, the top graph represents storm ID 10 and is an example of a clockwise rotational pattern where the concentration variable reaches its peak before peak discharge. The middle graph represents storm 21 and is an example of a counterclockwise rotational pattern where discharge reaches its peak before concentration. And the bottom graph 44 represents a counterclockwise figure 8 hysteresis pattern where more of this figure 8 style loop is created in the storm event. So hysteresis index and flushing index values were calculated for each event for both turbidity and total phosphorus, and then were represented by season. So this graph here, the colors are representative of specific seasons. The filled points represent the mean values for each of the variables in a specific season. And then the empty or hollow shapes represent individual storm events. Triangles represent total phosphorus, and circles are representative of turbidity for this figure.
3 minutes remaining.
Thank you. Statistically, there was no significant difference found between the hysteresis index and flushing index values for both variables across events and across seasons. But when visually inspecting this graph, you can see that spring and winter trend to have positive hysteresis index values, indicating clockwise rotational patterns and more proximal sourcing of these variables. And the summer and the fall having more negative hysteresis index values and more distal sourcing of these variables. The flushing index value calculated for all events except for on one occasion was always positive, indicating that there's also a concentrating effect of these variables in the 6 Mile Creek watershed. So to conclude, overall, the hysteresis index and flushing index values observed during storm events among turbidity and discharge and total phosphorus and discharge were behaving similarly across events and across seasons. And this is important because there wasn't a large difference in how total phosphorus and turbidity are behaving, or total suspended sediments in that matter, in the watershed. And due to that relationship, a better understanding and better monitoring setup for sediments in a watershed could be used to get an idea about how total phosphorus is behaving in that watershed as well. Also, the more positive hysteresis index values observed in the spring and the winter and more negative in the summer and fall could be driven by tile drainage influence in the watershed, with higher influence in the spring and the winter, as well as there being less crop cover and foliage to help stabilize the sediments, allowing for more rapid mobilization, where in the fall and the summer, there's a lower influence of this tile drainage and a higher influence of crop cover and foliage, giving that stability. Ultimately, the key to this research was high frequency data. And even though we had high frequency data for turbidity and discharge, a generation of a linear model was still necessary to handle the total phosphorus dynamics. And so moving forward in this research, having the availability of a sensor that could detect high frequency nutrient data on 15-minute intervals or higher could be a great step moving forward. I would like to thank and acknowledge the City of Bloomington, Joe Darter, Jill Mays, and Rick Twait for funding the research site at 6 Mile Creek and my research assistantship, and also give a shout out to the LEA Lab and all their students involved in the data collection for this project prior to myself. Here are some of my references. Thank you for watching and listening.